We concluded the last slide with an example of the MMC tolerance on an actual position for a hole. Okay, so what we want to do is a pin. Okay, so the last example, let's refresh our memory with the last example. It's a hole. So what we have is the virtual condition here. The hole is the minimum hole, which is 500 minus the 35 thousandths, which is 465. If we produced a hole at 503 and we subtract the 465, we get our 38 thousandths tolerance. Okay, so let's look at a pin example now. Okay, so our pin, we have a 375 pin. That's our MMC is 379. Okay, that's the MMC size is 379. We have a 28 thousandths positional tolerance at MMC specified. So our MMC is 379, but if we made that pin to 378, we actually pick up an extra thousandths, 29 thousandths. But in this case, what we have is we made the pin really at 376. 376, that gives us 2 thousandths. It gives us 3 thousandths extra tolerance here. So 379 minus 376, we get an additional tolerance of 3 thousandths. Our specified tolerance is 28. If we add our bonus tolerance of 3 thousandths to that, we get 31 thousandths. And then the other way to look at it is the virtual condition is 407. Okay, 407 would be the MMC of the pin plus the 28 thousandths. And then minus the produced size, which is 376, we've got 31 thousandths. So that's our allowable tolerance. So what it was is we made the hole 3 thousandths greater than the MMC, in which case we effectively added 3 thousandths bonus tolerance to our hole position. Okay, so how do we go about verifying positional tolerances? We could do this several different ways. One of them is we could use a coordinate measuring machine and collect data. So measurement machines and inspection software, or manual measurements. And what we do is we find the positional variation. We find the difference between the basic dimensions and the measured values. And we call these variations from true position as the delta coordinates, or delta x or delta y or delta z. Okay, so let's look at an example. We've got some examples in your homework assignment too of this. So here's how we would verify a position tolerance. Okay, we have our tolerance right here. We have our feature control frame right there. We have our datum reference frame, 3 planes A, B, and C, and we have 12 thousandths diametrical tolerance zone at MMC is applied. So here's our produced part. Okay, so 506 is what we actually made that hole to when it's measured to the datum reference frame, and then 496 is this dimension here. So these are the actual dimensions of the produced part. Okay, so we have a table over here. So for hole number 1, that hole was made at 191. Okay, its x coordinate is 506, that's this dimension right here. Its y coordinate is 374, that's this dimension right here. The basic dimensions that find those locations are 500, which is shown right here. So 500, and we actually ended up with 506. And then 375, which is actually 374 now. Okay, so the difference, the variation between the two is 6 thousandths in the x direction and minus 1 thousandths in the y direction. Okay, so we did that for all 4 of these holes here. We tabulated what the basic dimension is, we tabulated what the hole size is on this actual measurement here, and then we tabulated what the x and the delta x and the delta y dimensions are. Okay, so let's go over to the next slide. And really what we want to do is, when we're doing this, we got coordinate measurements to calculate the diameter of position tolerances consumed by a measured hole, and the measured coordinates made relative to the datum reference frame, and the measuring position variation must be less than the allowable position tolerance. Okay, let me say that again. The measured position variation diameter must be less or equal to the allowable position tolerance diameter. So here's how we get the variation, the diameter position variation. We take 2 times the square root of the delta x squared plus delta y squared. Okay, so let's look at this example here. I wrote this out for you. Okay, so how did I determine whether or not the position of hole 1 is good? Okay, just like the previous slide over here, what I need to do is to calculate both what the allowable variation is, what is the tolerance, and since this is at MMC, I need to consider the bonus tolerance. Okay, so our manufactured hole size is 191 for hole number 1. The MMC hole size here is given right here as 0.188. Therefore, I've netted 3 thousandths in bonus tolerance. Okay, so now my positional tolerance is 12 thousandths. That's the specification, plus our bonus tolerance of 3 thousandths gives me an allowable tolerance for this hole manufactured at 191 of 15 thousandths. Okay, so now to determine whether this part is good or not, I need to determine what the diameter of the positional variation is. And this was this equation from the last slide. So I'll take 2 times the square root of 6 thousandths, that's this 6 thousandths here, squared, minus 1 thousandth squared here. Okay, and that's what gives me is a position tolerance variation, of 12.2 thousandths. Okay, so now we know if the position is going to comply with the tolerance. The manufactured part is going to comply with the tolerance if the diameter position variation is less than the allowable variation. So in this case, my diameter position variation, that's this number right here, 12.2 thousandths, is indeed less than or equal to 15 thousandths. That is true, so therefore the position of hole number 1 is acceptable. I give you an example of this to work on for your homework assignment. And they set it up with basic tables like this. You should be able to figure out the tables. But this is how you go about doing it. For position calculations from coordinate measurements. Paper gauging. This would be another way of determining whether or not your holes are within tolerance. And really, I'm just going to introduce this topic. I'm really not going to talk about it too much. For your homework assignment, I just really want you to do the position calculations from coordinate measurements. The other way to check these would be with a functional gauge. That's another method for verification of hole positions. So the gauge is designed and fabrication can be costly. Okay, so it could be costly to build a functional gauge to check the position of those 4 holes. Gauges can reduce the inspection labor when inspecting many parts. That's why you would do it. You would suffer the costs of designing and building a functional gauge. If you had a lot of whole parts to inspect, because you could save time inspecting those parts. So if you put the part on a functional gauge and it'll determine that everything's good, it's going to save you some time over, putting the part on a coordinate measuring machine and taking all of these calculations and measurements and then making a bunch of calculations. And then process control of fabricating processes may minimize needed inspection. I want to start the next movie at slide 38 when we talk about advantages of positional tolerances. So that's the end of this slide of this movie. Thank you.